All right, so we're going to talk about like second order circuits. As I mentioned before, if we have like a first order circuit, what it means is that we're going to only have to deal with one storage element. Now we're just going to say, what if we have both capacitors and an inductor in the circuit? How can we deal with that? If you recall, if we had like a capacitor or an inductor, we ended up solving a first order differential equation. And now we have both of them. We're going to end up solving a second order differential equation, and hence the name second order circuit. So let me quickly define what a second order circuit is. And then given that, we can talk about like the first, second order like differential equation, and we're going to learn how to solve it. So definition, second order circuit. Second order circuits are the circuits that have a capacitor and an inductor. Again, does not really matter how many resistors we have, how many dependent sources we have, how many independent sources we have. But we only got to have like one capacitor or one inductor. Or at least like if we're simplifying it down, we end up getting one capacitor or one inductor. So it can have as many resistors, sources as we want. Right? And as I mentioned, to solve such circuits, we're going to end up getting a second order differential equation. So to solve for any current or voltage in the circuit, we need to solve a second order differential equation. In particular, we're interested in differential equations that look like this. dx squared dt squared plus 2 psi omega naught dx dt plus omega naught squared xt equals some f of t. Right? You might look at it and just be like, this looks a little weird. Why do we need to like call this 2 psi omega naught or like omega naught squared? In a second, it'll be clear why we're calling them those things. But you can think of them as like some constant value for all these coefficients. So this is basically some constant A, and this is some constant B. These two are constants. Right? And that f of t is a force function. Right? So let's do a quick example. If you recall, when we're doing like a first order, we said like if we have any circuit that has like a capacitor, we can have like that general form of like having a resistor followed by a capacitor, and we call that the most general RC circuit. And we said like we can basically look at the capacitor as our load and the rest of the circuit as the black box and replace it by the Thevenin equivalent. We can do the same thing here. We can basically look at both capacitors and inductors together and think of it as a load and the rest of the circuit as a black box, and have an example as this, which is my general case of an RLC circuit. So example, let's just say I have some source Vs of t followed by some resistor R followed by a capacitor C and some inductor L. Right? And what I can do is that I can basically think of this portion as my Thevenin equivalent. Right? Nonetheless, I can analyze this circuit. Right? It's not a very difficult circuit. Let's just call voltage across this R VR, voltage across this capacitor VC, voltage across this inductor VL. Do you agree I can write a KVL here? I have a single loop. I can go around and add up all the voltages. So writing a KVL, it tells me VR plus VC plus VL must be Vs of t. Right? Do you agree with that? Just go around and add up all the voltages. Let's call current through this loop here I of t. Right? Do you agree voltage across R, that resistor, is the value of the resistor times that I? That's Ohm's law. So VR is R times IT plus. Do you agree current through this C is still IT, and the relationship between I and V is I equals C dV dt? Do you agree with that? So how do I find V then? It's through the integral. It's through the inverse of the derivative, right? So VC is 1 over C integral from minus infinity to T I tau d tau. Let me give you like a quick reminder. Vc of t is 1 over C integral from minus infinity to T of IC of tau d tau. Right? What is VL? I know current through this inductor is I, and the relationship between voltage across an inductor and current through it is VL equals L di dt. So it's plus L di dt. That must be the same as Vs of t. You with me so far? Yeah? But look, I have an equation that has both integral and derivative. I cannot really solve such an equation, right? So I have to somehow get rid of that integral. How do we get rid of an integral? Well, we can take a derivative. Because of first theorem of calculus, I know if I take derivative of an integral, I'm going to end up getting the argument inside the integral, right? So I can take derivative. So taking derivative from both sides, what do I get? I have to take derivative of R times IT. R is a constant, so I can pull it out. I is a function that's changing over time, so I can take derivative of that. So I have R di dt, right? Plus 1 over C, derivative of minus infinity to t, I tau d tau, is I of t, right? So times I of t plus L, I have to take derivative of a derivative, which is the second derivative. So it's going to be L di squared t dt and that's d dt vs of t. Right? Now I have an equation that only has derivative in it. I can solve for it. But remember, like every time we're trying to solve a differential equation, we're trying to make the leading factor 1. So the leading factor is basically the coefficient of the second derivative here, right? So how can I get rid of that and make it 1? Well, I have to divide everything by L, right? So if I divide everything by L, this is what I get. I get di squared dt squared plus r over L dit dt plus 1 over LC it equals 1 over L dvst dt. Right? Look what we ended up getting. We ended up getting a second order differential equation, right? With the coefficients r over L and 1 over LC. Right? So if I compare it to this general formula that I have over here, this is basically this r over L is 2c omega naught, and this 1 over LC is omega naught squared. Right? So I end up getting a second order differential equation. So I got to be able to solve this second order differential equation and get the solution for this. Right? Let's do one more example. Let's just say I'm given a circuit that looks like this. I have this Is of t followed by some R, an inductor L, and a capacitor C. Right? Again, just like the first order circuit, we can think of this R, C, and L together as my load, and the rest of the circuit as black box. I find the Norton equivalent. So this over here could be thought of as my Norton equivalent. Right? Let's just call current through R IR of t, current through L IL of t, current through C IC of t. Do you agree if I write a KCL at the top node, I have this equation, IR of t plus IL of t plus IC of t equals IS of t. Do you agree with that? Whatever current I have going in must be the same as the current that's going out. Right? So I have that. Do you agree voltage across this C is the exact same as voltage across this inductor, is the exact same as voltage across this R? Yes? Why? They're in parallel. So let me call voltage across this C V. Do you agree I can write IR of t as this VT divided by R? Right? It's voltage across the resistor divided by the value of the resistance. So I have VT over R. Do you agree voltage across this L is also V? Right? So what is the relationship between I and V for an inductor? The IV relationship is again through integral. Right? So let me quickly give you a reminder. This time I'm going to actually write it in a very general term because I want to show you something. So instead of assuming my initial value is negative infinity, I'm going to assume the initial value is some t naught. So I can write this as 1 over L, t naught over t, t naught to t, VL tau d tau. Right? Remember, if t naught was negative infinity, we know IL of t is 1 over L negative infinity to t VL of tau d tau. Right? And essentially, I can use any of these, and you're going to see why in a second. But for now, I want to use like the one on the top. So instead of assuming my initial condition is happening at time negative infinity, I want to assume it happens at some time t naught. Right? So keep that in mind. So what is this IL of t? So IL of t is some IL at time t naught plus 1 over L integral from t naught to t v tau d tau. Right? What is I through this C? Well, I know voltage across it is V. Current through it must be the value of the capacitor times the derivative of the voltage. So it's plus C dV dt, and that must be Is of t. Right? Again, I ended up getting an equation that has both integral and a derivative. So I cannot solve it. To be able to solve this equation, I have to take derivative of both sides. So take derivative What is the derivative of the first term? Again, 1 over r is constant, so I can pull it out. So I have 1 over r dvt dt. So I have 1 over r dvt dt plus. What is the derivative of this IL at time t naught? That's a constant value. The derivative is 0. So it did not really matter like where it started. It did not matter if this t naught was negative infinity or some t naught that's given to you. Since that value is constant, when I'm writing the differential equation, I end up, ignoring that. Right? So I have 0 plus, what is the derivative of integral? It's basically the argument inside of it. Right? So it's plus 1 over L Vt plus C. I have to take a derivative of the derivative, so it's going to be the second order derivative. dt squared equals d dt Is of t. Right? Again, I ended up getting a second order differential equation, but I want the leading factor to be 1. So what do? I divide everything by C. Right? So if I divide everything by C, my differential equation becomes d squared v dt plus 1 over rc dvt dt plus 1 over lc vt equals 1 over c ddt of Is of t. Right? Again, I end up getting like a second order differential equation. If I compare it to the general formula that we had before, this term over here is 2c omega naught, and this term over here is omega naught squared. Right? In a second, I'm going to tell you like what these basic constant mean. But for a second, let's just like only focus on the differential equation. Right? So in both cases, we end up getting a second order differential equation. So the question comes down to, how do we solve a second order differential equation? right? So let's look at that. How to solve a second order differential equation. Again, remember the equation that we're dealing with is something like this. D squared dx of t dt squared plus 2c omega naught dx dt plus omega naught squared xt equals some f of t. Right? And keep that in mind. This differential equation that we're writing, x of t can be anything in the circuit. Right? Unlike the first order circuits that x of t must have been v across the capacitor or current through inductor, in this case, it could be anything. This x of t can be any current or any voltage in the circuit. So let me quickly remind you, x of t can be any current or voltage in the circuit. Right? But the idea is that I have a differential equation. I have a second order differential equation. I got to solve it. I know the solution for a differential equation that looks like this must have two portions. One, it's a particular solution, which is due to that f of t, which is our force. And one part, which is the complementary solution, which is the solution to the homogeneous differential equation, which basically means find a solution when f of t is 0. Right? So solution for this differential equation is x of t equals xp of t plus xc of t. We know xp of t is the particular solution, which is due to f of t. Xc of t is the complementary solution, which is due to the homogeneous differential equation. Right? Let's talk about the particular solution quickly. Just like the first order, finding the particular solution is by guessing. You have to guess what your solution is. And since that is the solution of this differential equation, that must satisfy this differential equation over here. We're going to plug it in there, and we're going to find like what that function is. In general, doing this is very difficult. Good news is, just like the first order circuits, what we're assuming is that f of t is either constant or a sine wave, which means the circuits that we're dealing with only got constant sources or sine wave sources. Up to this point, we only talk about like constant sources. Okay, so let's just assume f of t over here is also constant. Right? Let me quickly remind you to find particular solution xp of t. We assume f of t is either constant or sine wave. If it is constant, what it means is that xp of t is constant. If it is a sine wave, we know xp of t is also a sine wave. Right? So it's not that bad. How about the complementary solution, though? That is the important one here. To find a complementary solution, we have to solve the homogeneous differential equation, which basically means we have to like zero out f of t, right? So let's just see how we can actually solve that. To find complementary solution xc of t, we need to solve second derivative plus 2c omega naught dx dt plus omega naught x squared x of t equals 0. Right? You with me so far? We know the complementary solution of this type of differential equation is some constant times e to the power of st, right? The idea is that what is that s, right? So we know the solution of this differential equation has the form of xc of t is some constant k e to the power of s times t, right? So the question is, how to find s, right? Because as soon as I know s, I know like what the solution is, right? Remember, this xc of t is indeed a solution to this differential equation. So if I find the second derivative of this xc, find the first derivative of this xc, and plug it into this differential equation, that must satisfy this equation, right? So let me just quickly find the first derivative of this xc. So what is the xc dt? What is the first derivative of this? It's k times s e to the power of st, right? So it's k s e to the power of st. What is the derivative of the derivative, which is the second derivative of xc? What is it? K times s is constant. It doesn't change anything. What is the derivative of e to the power of st? Is s times e to the st, which is k s squared e to the st, right? And I know if I plug them in here, it should satisfy this equation. So let me quickly plug it in there. Plug it in. I have the second order derivative. So I have k s squared e to the st plus 2c omega naught first order, which is k s e to the st, plus omega naught squared x, which is k e to the st. That must be 0, right? I can factor out this k times e to the st. From the first equation, I have s squared. From the second equation, I have 2c omega naught s. From the last equation, I have omega naught squared. And the whole thing must be 0, right? I have two terms that are multiplied and gave me 0. What does that tell me? It tells me it's either this term or this term that is 0. I know k times e to the power of st is not 0. Therefore, what it implies is that this portion must be 0. So what it implies is that s squared plus 2c omega naught s plus omega naught squared, that must be 0. And this is a quadratic equation, so I can get two solutions for it, s1 and s2. And I can plug it in here, and that would give me like the solution. You guys have seen this equation before. That's a characteristic equation for a constant coefficient differential equation. That's a characteristic function. And that's basically how you drive that characteristic function, right? For us, we're not going to go to like higher order differential equation. So this is always our characteristic function, right? And now we know this is the differential equation. We know this is the characteristic function corresponding to this differential equation, right? It's a good time to define why we're defining this as 2c omega naught and this is omega naught squared. The reason behind it is that this c over here actually determines what kind of solution we have. And we call that the damping ratio. And this omega naught squared tells us if we have like a sine wave as our solution. Again, remember, we're not talking about like sine wave sources. We're talking about sine wave solutions, right? This omega naught tells me how my solution is oscillating. What is the frequency that my solution is oscillating? So let me quickly define what this means. So we define C to be the damping ratio which tells us what kind of solution we have, whether it is exponential or sinusoidal. And this omega naught, which we call it undamped natural frequency, which tells us how fast the sine wave oscillates. Right? In a second, you're going to see like why this damping ratio tells us what kind of solution we have. But before we get there, let me quickly give you a reminder as to how we can actually solve a quadratic equation. Remember, this is the equation that we need to solve, right? So let me quickly remind you how we solve such equation. If I have a quadratic equation like this, plus bs plus c equals 0, we know there are two solutions, and we can find s1 and s2, which are the solution of this quadratic equation, using this formula. Minus b plus minus radical b squared minus 4ac divided by 2a. Right? This is a general formula. I can absolutely apply it to this. Right? So assume A is 1, B is 2c omega naught, and C is omega naught squared, right? Which gives me this equation, right? I can find the solution to the characteristic function. So my characteristic function is s squared plus 2c omega naught s plus omega naught squared equals 0. So if I apply it, I get s1 and s2 to be computed using this. Minus 2c omega naught plus minus 4c squared omega naught squared minus 4 omega naught squared divided by 2. Right? Just applying that formula. I can factor out this 4 times omega naught squared, bring it out of the square root, which becomes 2 times omega naught. And I can simplify this and get S1 and S2 computed from this equation. Minus C omega naught plus minus omega naught square root of C squared minus 1. Right? Now, as you can see, this C can tell us what type of equation we have. If C is greater than 1, underneath that square root is a positive number, which tells us we have 2 real solutions. If C is exactly 1, what it tells me I have 2 solutions that are exactly the same, because this portion goes to 0. And if I have C that is less than 1, what it tells me is that I have a negative number under square root. So what I end up getting is a complex number, which I can write it in terms of a sine wave. Right? So that C indeed determines what kind of solution we have. So let's categorize these solutions. Let's assume this C is greater than 1 for a second. Right? If C is greater than 1, I have 2 real solutions. I know exactly like what my solution to the differential equation is. And we call that solution an overdamped. Okay? So case 1, assume C is greater than 1. Again, if C is greater than 1, I have a positive number under radical, right? What it tells me is that I have like 2 real solutions. So S1 and S2 are real numbers, and solution to differential equation is xc of t equals k1 e to the s1 of t plus k2 e to the s2 of t, which I know s1 of t, s1 is minus c omega naught plus omega naught c squared minus 1. S2 is minus c omega naught minus omega naught c squared minus 1. Right? Like these basically solutions. Right? We call this solution overdamped solution. This is called overdamped solution. So we have overdamped solution if C is greater than 1, which means we have 2 real solutions for the characteristic function. Right? How do I find K1 and K2? Well, it depends on the initial conditions that we have in the circuit, or in general in a differential equation. So K1 and K2 are found using initial conditions. If I draw this, basically what it looks like is something like this. This is my solution. Right? How about C equals 1? So let's call it case 2. Assume C equals 1. What happens if C is 1? What it means is that what I have underneath here is 0. So my solution S1 and S2 are exactly the same, and it is minus C omega naught. So what it tells me is that S1 equals S2 equals minus c omega naught. Let's just call this S, right? Because they're exactly the same, right? We know the solution xc of t is k1 e to the st plus k2 e to the st. But wait a minute. What just happened? I have two solutions that are exactly the same. So what it tells me is that like these two solutions are not independent of each other. So I have to make it independent. So what I need to do is to multiply the second one by a t. Right? Basically, if you find the Wronskian of like this, basically these two solutions, it's non-zero. Right? Which means like these two solutions are not dependent. Right? We call this solution xc of t is called critically damped solution. Right? And if I plot this, it peaks and it decays. But the main difference between critically damped and overdamped is that it is peaking much faster than overdamped, and it's decaying much faster. And it all happens because of that t that we're multiplying the solution with. Because of that t, we're peaking like much faster, and we're decaying like much, much faster. So critically damped solution peaks faster and decays faster compared to overdamped. Right? So what happened so far? That C, the damping ratio, was telling us what kind of solution we had. If the damping ratio was greater than 1, what it meant was we had like two separate real solutions, and we call that solution overdamped. If C was 1, we only have one solution. Well, we have two, but they're exactly the same, right? And we call that solution the critically damped solution. The last case is when the C is less than 1. If this C is less than 1, I have a negative number under square root, right? So case 3, assume C is less than 1. If C is less than 1, I have a negative number underneath here, which means my solutions must be complex, right? So what it tells me is that S1 and S2 are complex solutions. As a matter of fact, I know S1 as S2 conjugate, right? So I can write S1 as minus C omega naught plus I omega naught times 1 minus C squared. S2 is minus C omega naught minus I omega naught 1 minus C squared. See what I did? Over here, I have C squared minus 1, which I know it's negative. So I'm going to factor out a negative 1, right? So I have negative 1 times 1 minus C squared. But I know the square root of negative 1 as I. So that's how I wrote it this way. remember, this I is a complex number. This is basically the imaginary number, which I know I squared is -1, right? Or you can think of it as like square root of -1 as I, right? If you check your textbook, your textbook uses J instead of I. And if you check out like physics textbook, they use K instead. It depends on like what your background is. They either use I or J or K. My background is mathematics, so I use I. But it can use any of them. They mean the same thing, right? What's important though is that if C is less than 1, I have two solutions, and the solutions are complex, and we call this solution to be underdamped, right? Let's have a little bit of like notation here. It's a notation. Let's just call C omega naught sigma. And omega naught times 1 minus C squared omega t. This is what we define, right? Therefore, I can write S1, given this notation, I can define S1 to be minus sigma plus I omega d, and S2 minus sigma minus I omega d, right? I'm just doing it because I don't want to keep writing that long equation, right? It turns out the solution here, xc of t, is e to the power of minus sigma t, sigma is this, times some constant k1 cosine omega dt plus some other constant k2 sine omega dt, right? We call this solution underdamped, right? And obviously we need to find k1 and k2. K1 and k2 are found using initial conditions. Here's the question. How did I go from e to the s1, which is this, minus sigma plus I omega d, plus k2 e to the s2t, to sine and cosine? How did I do that? Keep that in mind. E to the power of it, what is it? What is it? A reminder. E to the power of it is cosine t plus I sine t. That's a Euler formula that you've seen in calculus. That's a Euler formula. Right? So if I have e to the minus sigma plus I omega d, the whole thing times t, that is e to the power of minus sigma t times e to the I omega d t. And I can write this as cosine omega dt plus I sine omega dt. Right? And since S1 and S2 are conjugate of each other, right? I'm going to end up getting the solution that looks like this, right? What this means is that if I plot xc of t, it means I have an envelope and I have some sine wave that's oscillating between that envelope. So if I look at it, I have this e to the power of minus sigma t. And I have this sine wave that's oscillating in between. That's basically how we interpret this solution. What's important, though, is that if sigma is less than 1, if c is less than 1, we're in an underdamped solution, which means we're going to have two solutions that are complex. And they're basically complex conjugate. What we're going to be doing next lecture, we're going to do a few examples, just solving differential equations, and see how we can actually apply these things to those equations. Any question? I'll see you guys Wednesday.